that Google's new quantum computer is proof for the existence of parallel universes.
Quantum computers could be even more historic than that.
In a staggering leap forward that stunned both the quantum computing world and the broader scientific community, Google's quantum AI division has reportedly cracked the long-standing enigma of the observer effect, a pillar of quantum mechanics that has confounded physicists for over a century. The breakthrough came from a series of meticulously designed experiments at Google's quantum core facility involving their Sycamore-class processors operating at previously unachieved levels of quantum coherence. What makes this discovery so significant isn't just the taming of a deeply counterintuitive principle of quantum physics, but the fact that it fundamentally redefines our relationship with observation, measurement, and the fabric of reality itself. Before we start, hit the like and subscribe buttons for more exclusive news. The observer effect, in its simplest form, describes how the act of observing a quantum system invariably alters its state. This means that particles like electrons or photons do not settle into definite positions or states until they are observed, making measurement an inseparable part of the outcome. For decades, this has posed both a philosophical and a practical problem. In the realm of quantum computing, where qubits exist in superpositions and entanglements, observation generally leads to decoherence, the loss of quantum information due to interaction with the environment or measuring instruments. This made sustained computation at quantum speeds fundamentally limited because the act of retrieving data from the system disturbed the very data being processed. Google's research team, led by a coalition of quantum physicists, mathematicians, and engineers, developed an advanced architecture they call core phase isolation, which enables a form of indirect observation that doesn't collapse the qubit state. Instead of measuring the quantum state directly, the system creates a dynamic holographic imprint of the qubit's configuration in an auxiliary quantum field. This auxiliary field, which acts as a non-invasive observer, allows scientists to extract meaningful data without disrupting the wave function. In practical terms, this allows the quantum system to evolve naturally while still being monitored, something previously considered impossible under conventional quantum mechanics. This approach leverages a complex interaction between topological qubits and time-symmetric entanglement paths, wherein the past and future states of a qubit can be correlated without a definitive collapse in the present. It's a concept that only recently moved from theoretical frameworks into physical experiments. Google's team achieved this by designing a system of braided quasi-particles that communicate information via quantum interference patterns rather than direct positional measurement. These patterns can be read out through non-local observables, essentially allowing the system to report on itself without being touched. The implications are staggering. By bypassing the observer effect, Google has opened the door to quantum computations of unprecedented scale and complexity. Quantum systems can now be left in extended superpositions for far longer periods, enabling deeper and more accurate calculations across disciplines, from simulating molecular interactions in drug development to solving intractable optimization problems in logistics, finance, and energy. More crucially, it shifts quantum computing from a fragile laboratory novelty to a robust and scalable platform for general-purpose computing. At the heart of this breakthrough lies a redefinition of what observation means in the quantum realm. Observation no longer requires a classical interface that destructively intersects with quantum reality. Instead, it can be reframed as a participatory interaction within a self-contained quantum framework. This opens philosophical questions as well. Does reality exist independently of observation if it can now be observed without interference? If measurement no longer collapses the state of a system? Does the boundary between potentiality and actuality dissolve entirely? These questions, once speculative musings in theoretical physics circles, now demand rigorous reevaluation. Google's Quantum Core initiative had long been suspected of working on novel entanglement-based protocols, especially after their 2022 milestone of achieving quantum supremacy in a practical setting. But even then, their systems were plagued by decoherence and readout errors. The new core phase isolation technique appears to be the culmination of years of work on fault-tolerant error correction and topological qubit architecture. These aren't standard silicon-based qubits, but rather exotic states of matter that exhibit remarkable stability under environmental stress. What Google has effectively done is craft a quantum system that resists the very processes that once made quantum observations so self-defeating. The breakthrough also casts a new light on time symmetry in quantum mechanics. By embedding their qubits in a framework that treats future and past states as entangled, Google's system seems to challenge the classical notion of temporal causality. This echoes certain interpretations of quantum mechanics, like the two-state vector formalism, which suggests that quantum events are influenced by boundary conditions both in the past and future. In this experimental setup, Google's team appears to have validated aspects of these controversial ideas by demonstrating computational output that reflects retrocausal consistency. That is, output data that suggests the system knew its future measurement states and evolved accordingly without decoherence. Engineers at Quantum Core have also hinted at the development of a new quantum operating system, tentatively named EON, specifically designed to operate within this observer-free computational paradigm. EON doesn't interact with quantum data in the traditional sense. Instead, it modulates entanglement paths and interference fringes to encode and retrieve information. Early demonstrations show EON managing up to 1,024 logical qubits with negligible error margins, a staggering leap from the prior limit of about 100 stable qubits. With this operating system, Google is preparing to move quantum computing out of the realm of experiments and into practical applications at scale. The entire experiment required unprecedented environmental isolation, taking place in a cryogenic chamber near absolute zero, surrounded by multiple layers of magnetic shielding. Quantum Core's Sycamore X processors operated within a synthetic vacuum, with background quantum fluctuations reduced to near non-existence. These conditions were essential for the sustained superposition states and entanglement pathways that made non-invasive observation feasible. But it's not just the engineering that's impressive, it's the elegance of the solution. Rather than force quantum systems to comply with classical logic, Google embraced the strangeness of quantum mechanics and built a new logical framework around it. Among the immediate beneficiaries of this breakthrough is the field of quantum chemistry. With the observer effect neutralized, simulations of electron orbitals, reaction dynamics, and quantum tunneling can now proceed without artificial limitations on observation time or resolution. Similarly, in the field of quantum artificial intelligence, systems can be trained within coherent quantum loops that evolve and refine solutions in real time without ever collapsing. This continuous evolution allows for forms of machine learning that are not just faster but fundamentally different, rooted in probability amplitudes rather than binary weight adjustments. Security and cryptography also enter a new era. Quantum cryptographic systems can now be designed that are not only unbreakable by classical standards, but dynamically adaptive to threats in real-time quantum space. Since observation no longer disrupts the system, intrusion detection in quantum communications can operate persistently, detecting the slightest perturbations across entangled channels without compromising the integrity of the communication. This lays the groundwork for a global quantum internet that is not just fast, but impenetrably secure. Physicists have long debated whether the observer effect is a fundamental limit of nature or a byproduct of incomplete understanding. Google's work seems to suggest the latter. By constructing a system that treats observation as a native quantum function, not an external act, they have reframed what was once thought of as a limitation into a feature. This echoes early philosophical positions from the likes of Wheeler and Bohm, but unlike those purely theoretical musings, Google has actualized them in hardware and software. Perhaps most remarkably, Google's breakthrough may have implications for our understanding of consciousness. If observation is not inherently tied to disruption, then the long-held analogy between conscious awareness and quantum measurement begins to fray. It opens new pathways for examining whether consciousness itself might be a form of non-collapsing observation, not influencing quantum states directly, but existing as part of a greater informational framework. Though speculative, such implications could redefine neuroscience, cognitive science, and artificial consciousness studies. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, What are your thoughts on Google cracking the observer effect? What could this mean next? We want to hear from you. Thank you for watching and see you next time.